feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instructional video here with Mr. Gaines as we continue our discussion on nonlinear systems of equations. In the last video, we took a look at possible numbers of solutions for nonlinear systems of equations and then took a look at how to solve those both algebraically and graphically. So let's continue some examples. So if we look in our notes in problem 2c, we are solving these equations algebraically and checking them graphically. So in 2c, the equations are set up rather nice for us. We see a linear equation and a polynomial, a quadratic equation. We can solve these, in this case, through substitution. So again, we talked about substitution primarily being the method that we're going to use to solve the equations. So we want to isolate a variable. In this case, both, if I label them A and B, both equations have y already isolated. So I can substitute one equation into the other, which essentially lets me set the equations equal to one another. So x squared plus 4x plus 3 is equal to 2x plus 6. Now, because this is a quadratic equation, I want to make sure that it's equal to 0 in order to solve. So I'm going to subtract 2x from both sides. I'm going to subtract 6 from both sides. We should see that this is going to be a fairly simple factorization into two binomials. So we have x and x that multiplies together to give me x squared. The next two numbers have to be factors of a -3, so a positive and a negative. And we would see that a positive 3 and -1 would work here. This would give me 3x through distribution and negative x that would add together to give me 2x, the middle term. So now I can take both of these solutions, or both of these factors, and set them equal to 0. So x plus 3 would equal 0, x minus 1 would equal 0. Subtracting 3, I'd get x equals -3, and adding 1, I would get x equals 1. Now, I do want to make sure that I get the corresponding y values, so I can substitute these back into, I'm going to go into equation B. I'm going to substitute into equation B to get y equals 2 times -3 plus 6, which would be -6 plus 6, or 0. So my first point is -3, 0. I'm going to substitute the other one into equation B as well, replacing x with 1 in this case, and I would get 8. So my second solution would be 1, 8. Now I want to check these graphically. So I can go to my graph. Under y equals, I can create two equations here. The two equations that I have are already set equal to y, so I can type them in as they are written, and then we can look for the intersections of those two graphs. So remember again that graphically, the solutions would be the locations in which these graphs cross. So we can see we have two intersections there. We could use the second trace intersect option here under the calculate menu. I'm on the first curve next to one of my intersections. I'm going to hit enter. It's going to jump me to the other intersection. I'm going to keep it close, or sorry, the other curve, the line here. I'm going to keep it close to that intersection, hit enter, and I'm not going to guess. I'm just going to hit enter, and it gives me the solution 1, 8. I could do the same thing for the other intersection, but I'm going to move my cursors this time closer to the other intersection, so it's going to pick up, the calculator will calculate that intersection, and see that I have -3, 0, and so we have the correct solutions here. So let's take a look at another example here, in which case that these equations are not set up currently for substitution. So I'm going to label them again, equation A and equation B. I'm going to set up equation A to isolate y. Again, I wouldn't necessarily need to do this to solve algebraically. I could just do B, because B is probably a little easier to isolate y, but I do want to be able to substitute this into my calculator and graph them. So in order to do that, I need y by itself. So if I add y squared to both sides and subtract x squared, I'm going to get y squared equals a -x squared plus 16. This is going to end up being a circle here. I'm going to square root both sides, and so I'd have y equals plus or minus the square root of -x squared plus 16. Then for B, I'm going to do the same thing, slightly different steps because it's a different equation, but I'm going to subtract x from both sides and divide by 2 to isolate y. So y would be 1/2 x minus 5. Now, again, if I want to solve this algebraically, I have the two set equal to y. I can substitute at this point. Now, I could have substituted prior to this. I could have taken this value for y and substituted into the equation b. But again, I wrote y, isolated y in case I wanted to graph. So here I can essentially set the equations equal to one another. So 1/2 x minus 5 is equal to plus or minus the square root of negative x squared plus 16. I want to get rid of that square root, so I'm going to square root both, or square both sides of the equation. So when I square 1/2 x minus 5, this is not going to be very nice, but 1/2 squared would be 1/4. X squared is x squared. I would have 1/2 times negative 5, which is negative 5 over 2, and then double that, so I'm going to get a negative 5x, and then I'm going to square the negative 5 to get 25. On the other side of the equation, the square and the square root are going to undo each other's operations, and so that's going to leave me with negative x squared plus 16. Here I have a quadratic equation, so I want to get this equation equal to 0, so I'm going to add x squared to both sides, so that would be essentially adding 4 over 4x squared. So I would get 5 over 4x squared minus 5x, and I'd subtract 16 from both sides, and this would give me plus 9 equal to 0. At this point, this is a quadratic, and I want to be able to solve this quadratic. It's probably a little easier if I can get rid of the fraction. So I'm just going to multiply all of this by 4. So I get 5x squared minus 20x plus 36 equal to 0. And when I look at this quadratic, I notice that c and b together, if I were to multiply them, would be a rather large number. So actually, before I even try to solve this, I'm going to look at the discriminant. Remember, the discriminant is b squared minus 4ac. And I want to see what this relationship is to 0. Is it going to be equal to 0 or greater than or less than 0? So I want to find that relationship. So I'm going to substitute in negative 20 squared minus 4 times a, which is 5, times c, which is 36. Now again, I want to find that relationship to 0. I'm doing this trying to make sure I have solutions. Now, you wouldn't necessarily need to, but here, if I take a look at the discriminant, let me evaluate all of that in my calculator so that you can see it. I get a negative 32, which is less than 0. So in this instance, the discriminant is less than 0, which means my solution is going to be imaginary. Remember, the purpose of solving a system of equations is to find the intersection point on the graph. So this is technically going to have no real solutions. It would have imaginary solutions, but in this instance, we're looking for intersection points on a graph, and so imaginary solutions are not really our focus right now. So if I want to check this graphically, I'm going to go back and again type in my equations. So 1/2 x minus 5 is going to be one of my equations. Another equation I'm going to do is the square root of negative x squared plus 16. And then remember, that was a plus or minus in front of the square root, so I'm also going to do the opposite of the square root of the opposite of x squared plus 16. And I'm going to put it in a square graph, zoom 5. Take a look at this. And we can see here that the line does not intersect with my circle. It's very close, but there is a gap between the line and the circle, and so this would have no real solutions. Take a look at some more examples. At this point, if you kind of get the process, see if you can pause the video and solve for E. Hopefully you've gotten a chance to work through E. Let's go ahead and work through that as well here in the video to see if we get the same solution that you got. So currently y is already set equal to or y is already isolated for equation A. So if you want to substitute at this time, you could. Again, I'm going to go ahead and rewrite b just for the purpose of graphing. So b would be negative 3x plus 8. That way it's prepared to graph when I come to that point. Now again, I have equation A and equation B where y is isolated, so I can substitute, which would essentially set the equations equal to one another. So negative 3x plus 8 is equal to negative 2x squared plus 6x minus 5. In this case, again, I have a quadratic, so I want to make sure the quadratic is equal to 0. So I'm going to add 2x squared to both sides. I'm going to subtract 6x from both sides, so that's going to give me a negative 9x. I'm going to add 5 to both sides, so that's going to give me a 13. So I have 2x squared minus 9x plus 13. Now let's go through the process of solving. Maybe you looked at the discriminant in this one, but I'm going to go through the process of solving. I may notice that this is not easy to factor. I have a leading coefficient other than 2, so I don't want to complete the square, most likely. And it's not set up in vertex form, so I'm not going to use the square root formula, square root property of equality. I would use the quadratic formula here. So the quadratic formula would be negative b, my b is 9, or negative 9, so negative negative 9 would be positive 9, plus or minus the square root of negative 9 squared minus 4 times my a would be 2, times c would be 13, all over 2a, or 2 times 2. So you could have checked the discriminant in this to see if you're going to have a solution. But if you didn't, that's okay as well. And I'm just going to go under the assumption that you didn't. If we don't check the discriminant and we get into the solving process, if I simplify inside my root, I'm going to come up with a negative 23. And at this point, we can go ahead and stop the solution process. Yes, we could simplify this and give imaginary solutions, but we are looking for the real answers here for this system of equations. We're looking for the intersection points of the solution. So there are, or of the system. So there are no real solutions here. If we were to graph again, we can graph this. I can graph by typing in my two equations. So A was already written with the y variable being isolated. B, we isolated the variable on our own. And as I graph those, I can take a look and see that the graphs do not intersect there. The line and the parabola have a gap between them, and they will not intersect. So we have no real solutions. Go ahead and pause the video and see if you can complete F. So for F, the process is the same here. I'm going to go ahead and forego the graphing process. I'm just going to forego the graphing process. And if you wanted to graph this, you would need to rewrite equation A. I'm just going to go ahead and go straight to substitution. Okay? So I already know that y equals x, and so I'm going to take b and substitute that directly into A. So I would have y replaced by x. So I get x squared plus x squared equals 4. So then I would add my x squareds together, so 2x squared equals 4. Divide by 2, x squared equals 2, so x equals plus or minus the square root of 2. So I'm going to have two solutions. One is going to have an x value of positive root 2. The other is going to have an x value of negative root 2. The y values can be found fairly easily here. If I substitute into the equation for b, I already know that y is equal to x. So if x is positive root 2, y has to be positive root 2. And for the other option, if x is negative root 2, y has to be negative root 2. And so there I have my two solutions. Now, when it came time, if I wanted to graph these, y equals x is prepared to graph. On the other one, I would have to rewrite equation A. And so that would be y squared equal to negative x squared plus 4. And that would give me the plus or minus the square root of negative x squared plus 4. So I could input both of those into my calculator. So the positive root of negative x squared plus 4 and the negative root of negative x squared plus 4. Graph those, excuse me, and see that there are two intersections. Now I did do this in the rectangular view of the graph, and so I can see it kind of looks like an oval, but if I were to change my zoom to the square version of the graph, it would look a little bit more like the circle graph that it is. Now I do need to find those intersections, so second trace, that takes me to the calculate menu, choose intersect. I'm going to move my cursor over close to the first intersection in the upper right, go through the process, and it gives me 1.414236 for x and y. If I were to take a look at what the square root of 2 is, it would be approximately 1.142136. So I'm going to go back to my graph now. I'm going to find the other intersection. Now this is going to be another step we have to do in the calculator, so I'm going to hit second trace intersect. I'm going to move my cursor down over here to the bottom left. Actually, let me zoom in a little bit so you guys can see this a little better. Oh, sorry, I just zoomed out. Let me zoom in 2 times. Sorry about that. Here's my original window, and now let me zoom in so we can take a better look at the intersection point here. So we can see our second intersection is down here, so I'm going to hit second trace, go to the intersect option. I'm going to move my cursor down close to the intersection we're looking for, hit enter. Now notice that my cursor's up on this top curve. So in my equation I had to put in 3, or in my calculator I had to put 3 equations. So I need to push the down arrow key to move it to the bottom curve. Now I can find that intersection and find out that it is negative root 2, negative root 2. So there we have both solutions for f. And this looks like a good place to stop. So here we have worked through just some algebraic and continuation of algebraic and graphic solutions for solving nonlinear systems of equations. In the next video, we'll take a look at a couple more examples, and then we will get into applications. As always, thank you guys for tuning in. I'll see you soon.